welcome to lecture number 28 of fuzzy sets, logic and systems and applications. So, in this lecture we will discuss a fuzzy relation. Before we move to fuzzy relation, let us first understand the crisp relation, because this is very important for understanding fuzzy relation. And crisp relation also, we need to know first the Cartesian product of crisp sets. So, if we have two arbitrary crisp sets with the universe of discourse capital X and capital Y respectively, the Cartesian product of A and B can be written as the A cross B, and this will be equal to the set of all pairs of X and Y such that X belongs to capital X and small y belongs to capital Y. So, this can be understood better by this example. Of course, this is a very basic understanding. You must have done this in your earlier classes of mathematics, but here this becomes little important to understand before we move to the crisp relation and then the fuzzy relation. So, if we take an example here where we have A and B two crisp sets. You can see here A is a set, is a crisp set where we have two elements in A 0 and 1, and in B crisp set we have three elements A, B and C. So, if we are interested in finding the Cartesian product, what do? We simply we multiply or we take the cross product of the two sets A and B, and this is going to give us the ordered pair of all the elements from A and B. So, but it should be within the universe of discourse. So, if I have to, let us say, find A cross B, this is going to be like this, like A cross B is going to give us a set which will contain X comma Y, means all the elements in the pair is coming from the set A and the Y is coming from the set B. And of course, this X and Y forms a pair here, and small x is from the universe of discourse capital X, Y from the universe of discourse capital Y. And we all know that in Cartesian product of two sets, crisp sets, we follow the order of the elements while making the pairs here. So, the first element will be from the set A, and then the second element of the pair will be from the element B, and then we collect all the formed pairs in the set, and this is A cross B. Now, when we are interested in finding B cross A, this will be a set of all the pairs of Y and X, means all the pairs here where the first element is coming from the set B and then the second element will be from the set A. So, here this is to be noted that the order is very important in the Cartesian product, the order in which the pairs are formed. Like in A cross B, we have x comma y, as a pair, but in B cross A we have y comma x as a pair, right. So, similarly, if we are interested in finding the A cross A, you see here that all the pairs will be like this, like both the elements will be from the set A. Similarly, if we are interested in finding the B cross B, so we will have the collection of pairs in this Cartesian product set, and all the elements will be from the same set B. And of course, it is needless to say that they will have to follow this y x and y will have to follow the condition of universe of discourse, means x should be from the universe of discourse capital X and small y from the universe of discourse capital Y. So, here in this example, if we see that A cross B as we have defined here, if we take A set like this, like A has 2 elements 0 and 1, B has 3 elements A, B, C. So, we see here that if we take the cross product, if we take the Cartesian product here as A cross B. So, Cartesian product of the set A, please understand that this set is a crisp set. So, once again I am saying here that the Cartesian product of crisp set A and crisp set B is going to be all the ordered pairs that are formed elements from A and B. So, we see that A cross B is going to give us first pair 0 A, second pair 0 B, third pair 0 C, and then the fourth pair is 1 A, fifth pair is 1 B, sixth pair is 1 C. So, we see that we have 6 elements when we are taking the Cartesian product of capital A and capital B, where these capital A and capital B are 2 crisp sets. So, this way we get the Cartesian product of 2 crisp sets. Now, let us change the order and let us find B cross A. So, we write B here first and then we write A, and as we know that B has 3 elements A, B and C and A has 2 elements. Let us now find the Cartesian product of crisp set B and crisp set A. So, here we will first start with this element A, and this element will combine with all the elements of set A. So, this is going to give us A comma 0 as the first pair, and then the second pair will be A comma 1 here. So, like that we will be getting other pairs. So, we will have then B comma 0 and then B comma 1, and then finally, with C we are going to get C comma 0 and C comma 1. So, this way we are getting 6 elements in the set which is the Cartesian product of B and A. So, what actually we are doing here is that we are forming the ordered pairs of the elements that are coming from the first set and then the second set. And please understand that these pairs will belong to the universe of discourse that are created by the Cartesian product of the separate universe of discourses capital X and capital Y, or in this case if we take Y first then capital X then Y cross X. So, here this B cross A is, if we see that we are getting a set of 6 pairs of elements. So, we can clearly say that B cross A that we have seen here is different from A cross B. The order is changed. So, that is why we can say that A cross B is not equal to B cross A. Now, let us find A cross A. So, in A cross A, on the same lines if we move, we see that A cross A we are getting as, because in A we have two elements 0 and 1. So, we first take 0 and then we combine, we make pair of the elements that are written here in the other A. So, we have two sets A, and when we take the Cartesian product we are getting 4 elements, and these 4 elements basically we having elements from the same set A. So, we get 0 0, then 0 1, then 1 0 and then 1 1. So, this way we get A cross A. Now, let us find B cross B. So, when we are interested in finding B cross B, means we are taking two sets, both the sets are B and B only. So, when we make pairs of the elements from the first set as B and the second set also as B. So, we see that we are getting here 9 elements like this. So, A, AB, AC, BA, BB, BC, CA, CB, CC. So, like that we have 9 pairs of elements from B set only. So, this way we have seen that we can get the Cartesian product of B and B, and as we have already seen that the order is very important while we make pairs. So, that is why the Cartesian product of A and B is not equal to the Cartesian product of B and A. And please note that these two sets A and B are the crisp set here. So, this we have already seen that A cross B was coming out to be like this, and then B cross A is coming out to be this, and that is how we can, with example we can see that A cross B is not equal to B cross A, and it is because of the order in which the pair is made. So, in A cross B the first element of the pairs are coming from crisp set A, whereas in B cross A the first element of the pair is coming from the set B. So, that is why when we compare A cross B and B cross A, these both of these are not equal to each other. Now, let us move towards the Cartesian product of the n crisp sets. So, in general we can write the Cartesian product of the arbitrary n crisp sets like this, like A 1. If we represent the n crisp sets like this, like A 1, A 2, A 3 and so on up to A n. So, we can see here, and then if we are interested in Cartesian product of all these n crisp sets. So, we can say this is the Cartesian product of A 1, A 2, A 3 up to A n can be represented by the A 1 cross A 2 cross A 3 and so on cross A n, and this is going to be equal to set of all the elements x 1, x 2, x 3 and so on up to x n, such that the x 1 is from capital X 1 and small x 2 is coming from capital X 2 and so on, small x n is coming from the capital X n. So, in other words we can say that the cross product of n crisp sets A 1, A 2, A 3 up to A n is nothing but the collection of n tuples x 1, x 2, x 3 and so on up to xn. So, all such n tuples will be there in the Cartesian product when we take the Cartesian product of n sets and crisp sets. So, when we represent a Cartesian product like this, now this Cartesian product contains all the n tuples that are formed from the elements that are coming from A1, A2, A3 and so on up to An. And please understand here that these n tuples will belong to the universe of discourse, the capital X1 cross capital X2 cross capital X3 and so on cross capital Xn. So, when we have the Cartesian product, which is nothing but the ordered n tuples here in case of the Cartesian product of n crisp sets. Now, let us understand the relation among the crisp sets. So, here when we are interested in finding the relation, so normally we say the Cartesian product set is a relation set, but here we need to know that relation set is based on certain conditions. So, this I will be discussing in the next slide, but before that I would like to define the relation set by Q of A1 here, Q of A1, A2, A3 and so on up to An. So, this is here, this Q denotes the relation set, and this relation set will always be a subset of the Cartesian product of the A1, A2, A3 up to An. So, relation set of A1, A2, A3, An is a part of the overall Cartesian product of the sets A1, A2, A3 and An. This can be understood by an example here. So, let us take an example to understand the crisp relation. So, here we are taking two crisp sets A and B, and let us first find the Cartesian product of these two sets. So, A cross B can be written as the collection of all the pairs of the elements from A and B sets, and this way A cross B is going to be a set here, the Cartesian product of A and B. So, we see that we have here, since we have 4 elements in A and 3 elements in B crisp set. So, we are going to get 12 pairs here like this. Here the first pair is 1 2, second pair is 1 3, third pair is 1 4, fourth pair is 2 2, and like that we get the 12th pair is 4 4. So, this set contains all the order pairs which are possible out of the Cartesian product of A cross B. So, we see that this is the overall space, overall population that is possible here as the Cartesian product of A and B. Now, let us see what is a relation if we are interested by putting some condition. So, let us say we are interested in a particular relation, and the relation here is that we are interested in a set, let us say Q A B. So, this is a relation set, and this defines some relation based on some condition. So, Q A B is based on the condition here is that first element is greater than. So, first element of the pair that are formed is greater than the second element in the Cartesian product of A and B. So, we have already seen that we have Cartesian product here, where we have 12 pairs. Now, we are putting the condition that the first element in all the pairs should be greater than the second element. So, if we put this condition, we will find few pairs where this is true. So, if we are putting this condition and based on that we pick those pairs for which this condition is satisfied, and QAB relation is based on that condition. If that is true, then we can write QAB is equal to a set of these 3 pairs for which the first element is greater than the second element. So, we can see here that we have 3 pairs, that is 3 2, 4 2, 4 3, where the first element of the pair is greater than the second element in all the 3 pairs. So, QAB represent here a relation set, and we see that this QAB is coming from the total population, which we have got from the Cartesian product of A and B. So, Cartesian product of A and B is here, and Q of AB is here, and we can clearly see that 3 2, 4 2, 4 3, all these 3 pairs are drawn from the Cartesian product of A and B. After applying the condition, the first element is greater than the second element. So, since Q of AB is a set and it has some elements which are drawn from the Cartesian product of crisp set A and B. So, we can write here that QAB is the subset of the Cartesian product of A and B, where A and B both are the crisp sets. So, this way the statement that I made in the previous slide, that the relation, you can say here, the relation QAB is the subset of, here the relation set is a subset of the Cartesian product of the sets. So, this way we can write that relation set, the relation set is always a subset of the Cartesian product, or in other words, if we say the relation set in between A and B here in this case is subset of the Cartesian product of set A and B. Now, let us take another example here, where we take crisp set A and crisp set B here, and we have the universe of discourse here as for A we have capital X and for B we have capital Y. So, in this example we are supposed to first find the Cartesian product of crisp set A and crisp set B, that is A cross B, and then we are supposed to find the relation matrix Q1 of A comma B such that the first element is greater than the second element, as we have seen in the previous example. So, this very easy, we can first find the Cartesian product, so that we have the space, the whole population of the Cartesian product, and then from that we pick the elements based on the condition that is given, and this will be our relation matrix Q1 A comma B. And then next, in the third case, we are supposed to find relation matrix Q2 A comma B such that second element is greater than the first element. So, here based on another condition, we are supposed to find another relation set Q2 AB, and based on that we can find a relation matrix. In the fourth case, we are supposed to find Q3 AB such that first element is equal to the second element for A cross B. So, let us now quickly move ahead and first find the Cartesian product of set A and set B. Here both the sets are crisp sets. So, A cross B, as we have already done, we can quickly find here a set like this, and this represents the Cartesian product of this set A, where we have 4 elements 1, 2, 3, 4, and then we have set B, where we have 3 elements 2, 3 and 4. And A cross B, the Cartesian product of A and B here is the collection of all the elements which are ordered pairs. So, collection of all the ordered pairs of the elements coming from set A and set B respectively. So, we are getting here 4 into 3, that is 12 ordered pairs as elements of the Cartesian product of set A and set B. Then when we have this as the whole population here of the ordered pairs that are possible, now let us go ahead and apply the condition for the first relation. So, for the first relation Q1 AB here, Q1 AB, let us apply the first condition. First condition here is that the first element is greater than the second element. So, first element is greater than the second element means we have to look into all the ordered pairs for the first element, which should be greater than the second element in the same pair. So, we find here 3 pairs as elements of this set Q1 A comma B. So, Q1 A comma B is giving us 3 ordered pairs, where we see that the first element is greater than the second element. No other pair in A cross B in the Cartesian product of A and B is giving any pair which satisfies this condition. We can see here one by one. So, we see we have the first pair 1 2, where 1 is less than 2. So, the first element is less than the second element. So, this is not qualified. Then if we keep moving ahead, we see that here 3 and 2 satisfies the pair which is consisting of 3 and 2, which gives us this condition satisfied. So, we have collected this element here, and then 4 2 is another pair which satisfies this condition, and then we have 4 3 also which satisfies this condition. So, this way we get 3 elements here in this set Q1 AB, which is relation set, where the first element is greater than the second element. So, this is how the relation set is formed by the crisp sets. Now, let us form a matrix here. So, relation sets can also be represented by the relational matrix. So, if we have A like this and B like this, like we have rows and columns, and based on that the relation we can write in form of matrix. So, we see Q1 A comma B. So, we have 3 2 4 2 4 3. So, if we write 1 2 3 4 as a column and then 2 3 in the row. So, we see that we have 1 here, we can write here 1 because 3 2 is existing as pair in Q1 A comma B, and then we have 4 2 and then we have 4 3. So, in this Q1 relation set we have only 3 elements. So, we have only for this we write once, otherwise all other elements will be 0. Here this has to be noted that why are we writing 1, because the logic is Boolean logic. So, since this pair is completely present, so that is why we are writing 1 for all the existing pairs and 0 for non-existing pairs. So, that is why we have this matrix here as the relational matrix. So, this is Q 1 A B, Q 1 A B. Next is when we apply the second condition that was given, and this relation set is represented by Q 2 A comma B. So, we already have the set of the Cartesian product of set A and B here, and now we look for the pairs which satisfy this condition. What is this condition? Condition is that the second element is greater than that of the first element. So, we see that here we have got 1 2 as the first pair which satisfies this condition. So, first pair in Q 2 A B. So, Q 2 A B is the set of all such pairs which satisfy the condition of the second element is greater than the first element. So, 1 2 is the first element of Q 2, and then we have 1 3 also this pair which satisfies this condition. Then we have 1 4 which also satisfies this condition, and then we have 2 2 which is not satisfying this condition because 2 and 2 both are equal. So, here the second element is not greater than the first element. So, this is not satisfying, and then 2 3 is satisfying the condition, 2 4 is satisfying this condition. Similarly, we see that here 3 4 is satisfying the condition. So, this way we see that we have 6 elements, or I would say the 6 pairs in Q 2 A comma B, means the relation set Q 2 has 6 elements which satisfy this the given condition, that is the second element is greater than the first element. So, let us form a relational matrix. So, as we have done this in the previous case, so we can write a relational matrix like this, like we have 1 2 existing in Q 2 A B. So, we take 1 2 here and we see that for 1 2 we have written 1, and please understand that the column here is coming as the set A and the row as the set B. So, since we have 1 2 pair already existing in Q 2, so we write here 1, and similarly for 1 3 we write here 1, and then 1 4 we write 1, and then 2 3 we write 1, 2 4 we write 1, and 3 4 we write 1. So, all these 6 elements now have been represented in the form of a matrix, and this way all these elements have been included in the Q 2 A B set. And since no other element exists apart from these 6, so for all other elements, for all other combinations we are writing 0, and this way we have written the relational matrix Q 2 A comma B. And now we have to find the Q 3 A comma B based on the condition the first element is equal to the second element. So, since we already have the Cartesian product of set A and set B, and we apply this condition, the condition that is given, which is first element is equal to the second element. If we apply this, so we get 2 2 3 3 4 4 the pairs as the elements of Q 3 A comma B here, and which satisfies the condition that first element of these pairs is equal to the second element. So, Q 3 A comma B has 3 elements only 2 2, 3 3 and 4 4. So, first element, second element and then the third element, and this 2 2 is coming from here, 3 3 is coming from here and 4 4 is coming from here. So, this way we have another relation set Q 3 based on the condition that was given, and now further we can write this in form of a relational matrix. So, this relational matrix can be again on the same lines we can write. So, we see that since we have 2 2 present. So, for 2 here and 2 here, since 2 2 is present in Q 3. So, these two are forming one pair. So, we are writing here 1 and then we have 3 3 3 3 means 3 of set A and 3 of set B. These two also are forming one of the elements of Q 3. So, we are writing 1 and then 4 4 also. So, we see that here writing 1. Now, since we have only 3 elements, no other elements are present in Q 3. So, all other elements will be put as 0 of this matrix, and this is called a relational representation of Q 3 A B based on the condition, that is the first element is equal to the second element. So, this way we have seen that as to how we can find the Cartesian product of two crisp sets, and from the Cartesian product of the two sets based on certain conditions we find the relation matrix, and based on the certain conditions we find the relation set, and this can be represented in the matrix form. So, we call this as the relational matrix, and also the relation set that we get here is always the subset of the set which is coming out by the Cartesian product of the sets. So, in today's lecture we have understood that how do we find the Cartesian product of two crisp sets, and then how do we get the relation set based on certain conditions, and we have seen this by taking couple of examples, and this way we have understood the Cartesian product and relation and then relational matrix, and in the next lecture we will continue with the fuzzy relations. Thank you.